right, today we're going to talk about specific heat capacity. Um, Check the other two previous videos if you are interested in the difference between heat and temperature. I'm sure we'll mention it again anyway, but yeah. So this concept of heat is kind of interesting. Heat is, if you want, a form of energy, okay? So let's do a little recall about what energy is. Well, first of all, we need to talk about work, okay? So work in physics is defined as being equal to FD. And then, if you happen to not be putting your force in the same plane that direction is acting, you got to cos theta that, okay? So let's think about work in action. What if I take a box and let's say there's no friction. And I apply a force to the box in this direction, and I apply this force for some distance. Let's actually put some numbers in here. Let's say that that's 20 meters. Let's say my force is 100 newtons. And we'll say that we're working in the exact same plane, right? So I guess we'd say that's cos 0, which should be equal to 1. Okay, so all of the work that we're doing, pushing for this distance, is going into making this box do what? What would the box do? It's frictionless, and we're pushing on it over a distance. What would happen to the box? Well, not only would it move, right, it would accelerate, okay? So that means that its velocity here is much higher than its velocity was there. So the work that I did went into doing what to this box? Accelerating it or giving it something. What did it give it? It gave it kinetic energy, okay? Kinetic energy, now remember, we're in magic world where this is frictionless, and this is supposed to be a horizontal surface, and my goodness, did I ever not draw it very well? You know what? Just to make myself feel a little bit better, that this wasn't drawn by like a 4-year-old child, let's just cheat. There we go, look at that. Beautiful surface. I'm getting distracted by my messy drawing, right? Neatness is very important, especially in physics. Bad handwriting, incomprehensible diagrams, kill ya. All right, so let's do some math here. So the work I did, we said that we applied a 100 Newton force over a 20-meter distance. So we should have 2000 or 2000 Newton meters worth of work. We're going to disobey thermodynamics, and we're going to say all of that work went into kinetic energy in this box. Now it has some velocity. We know that it has 2000 Newton meters worth of work in it, and that must manifest itself as EK. And remember, the way to figure out what EK is 1/2 mv squared. So just to continue on this train of thought, we know that all of the work got converted into potential energy, kinetic potential energy. So therefore that must equal 2000 Newton meters. And if you look, the two unknowns that we have here are mass and velocity. So if we have a little mass, we're going to end up with a high velocity. If we have a large mass, we're going to end up with a low velocity. And that should jive with what you already understand, right? If this mass is very large for a given force, the acceleration will be smaller, and therefore the final velocity will be smaller, okay? So it's essentially another way of looking at this system. Okay, this is kind of the general basic way of thinking about work and energy, okay? So this is one way to give it kinetic energy. The other thing we could do is we could lift this up, thereby giving it gravitational potential. Now, I won't beat that to death. That's the concept behind this. So where does heat come in? Well, in reality, there's really not going to be a way for you to have a frictionless surface. So let's imagine a slightly different scenario. where, look at that, it's not that box, where now I apply a force, okay, to the object, but there is friction involved, okay? So let's say I push it along for the same amount of distance, I did 100 newtons, okay? Moved it along some distance, and then I stopped pushing, and I noticed that the velocity of the box when I stop pushing instantly or nearly instantly drops to 0. Okay? Did I do work in this scenario? Okay, but I have no kinetic energy at the end. Where did you go, kinetic energy? What happened here? If I obey the laws of conservation of energy that we should have kind of covered before, if I do work in one place, okay, that must mean that energy is stored somewhere else, or some energy is somewhere. We can't create or destroy energy. So in this scenario here, okay, the work turned into kinetic energy, but in this scenario, we have no kinetic energy at the end. So where did our work go? And you would tell me that it went into, good, friction, sound, and then friction actually is basically creating heat, right? Friction is a way of creating heat. It's if we want, depending on the scenario, we might consider it to be an unwanted place where energy is wasted. Okay, sometimes we want heat, depends, but in this case we probably don't, right? So in other words, when we examine the differences between here and here, what we might find is you would have a warmer object over here than you did over here. In other words, some of the work that you did went into the rubbing of the particles in these two surfaces together, thereby giving them, the particles inside of here, some individual kinetic energy. So we don't get kinetic energy as the box as a whole, all the particles moving in one direction. We get random kinetic energy of the particles in the block and also the particles in the surface. Okay, so some of the work we did went into actually giving or making these particles inside the surfaces move faster. So that's one concept or way of thinking about how we can get heat energy into an object, right? Physically rubbing the objects together requires work and manifests itself as a hotter object. So kinetic energy of the particles go up. Are you with me? Okay, so heat is the work to make something hotter. What about temperature? Where does temperature figure into all of this? So, oops. So let's think about that quickly. So let's say we have two objects on a surface, and let's say we have this surface over here, okay? And we do the same thing. We push the object over, but what if this surface, what if this surface is, say, smoother? Like its coefficient of friction is lower. It's a smoother surface, okay? What might we notice when we're putting in this amount of energy? What's one thing that could potentially happen if it's smoother? What might we be left with over here? Maybe some kinetic energy, sure. If we put the same amount of work in, we might notice that the object isn't as hot, right? It's possible that it isn't as hot when we get over here, and so on. What's that? It would be easier to push, sure. So we might have reduced the amount of force on the object, and so on. So there's sort of a some stuff to think about, like what are these surfaces like? How much friction is there existing between them, and so on. And that will tell you a little bit more about what the final state of the object will be like. Okay. Now let's talk about heat itself and different types of materials. So let's say we have three types of material. Okay. And let's say that they all have the same mass. We'll say this is a block of some kind of metal. Let's say it's a block of, I was going to say iron, but I don't have information for iron. So let's change it and make it copper. Plus that looks kind of like a copper color. Okay. And then let's say we have a block of aluminum. What has a higher density, copper or aluminum? Copper does. So therefore, just to be kind of like politically correct, let's make the aluminum block look a little bit bigger than the copper block, because we want to indicate that the aluminum has a larger volume for the same mass. We want to say that all the masses are the same. And let's actually even throw water in here. So we'll also have a cup of water of the same mass, and it would be lighter than all of those together. So let's make it a big mass of water. Okay, so there we go. Now, over here we were talking about putting heat in mechanically, right? But now let's talk about using some release of chemical energy and putting the heat in using conduction or convection, depending on how you want to call it. Or we could even, something we could do is we could embed some wires into here, right? And maybe put like a heating element right inside the block, assuming that this is sort of insulated away from the metal. And we could put a voltage through there and we could run current, and this could heat the block from the interior, or we could heat it with, a flame, right? Or we could put it on the stove on a heating element, or so on. Now let's say we have a very good way of monitoring how much energy we're putting in, right? So exactly how many joules of energy we're putting in. Oh, and that's one thing I forgot to mention. I was calling these Newton meters over here, just to help clarify where they come from. But the Newton meter actually has a name, and that is the joule, right? We call it the joule. That's the unit of energy in SI, and we've covered that, to death before. But just reminding you. So let's say at the beginning of our little experiment here, before we put any energy in, all of these are at 20 degrees Celsius to begin with. Okay, they're all at room temperature. All right. Let's think about the kinetic energy, distributions that we're going to have here. So for copper, right, we have our particles distributed like that, such that their EKs are gathered around that 20 degrees Celsius, EK particle, number of particles here. And we can have the same thing for our other substances. Okay, still very similar. And water. Okay. Alrighty. Now, if I put the same amount of energy into each of these, would you expect that their final temperatures, now assuming their masses are all the same, all the masses are exactly identical, okay? Before we actually do that, if their masses are identical, does that mean they all have the same number of particles within them? No, because the particles themselves weigh different amounts. Water has the lightest particles, so there must be more of them, right? There's also the concept of density, so it's not just about the number of particles, it's how close those particles are together, right? And we'll also notice that these are solids and this is a liquid, right? So they're in different phases. So there's a lot of variability here between these things. So the question is, if I put the same amount of energy into them, should they heat up the same amount? And your probably gut reaction is no, they should not. And you'd be absolutely right. So how much does their temperature change, and how can we predict that? So before we start, I'm going to ask you, which one of these do you assume is going to increase its temperature the most? And let's actually put some numbers in here. Why don't we say each one of these is 100 grams, say, or 0.1 kilograms. Each one's exactly 100 grams. And let's say we put 1 kilojoule of energy into each one, okay? So however we do that, we don't really care, either with a candle, electricity, we could even like maybe shine some light on it or whatever, right? We just know that we've put this much electricity into each one, 1 kilojoule. Which one do you think is going to have the highest final temperature after this? Pause there while you think about it. So we had a few guesses on which would be hottest, and just to kill the suspense, I'm going to rank them in order. The hottest one, after going from 20 degrees Celsius and having 1 kilojoule added to it, would be copper. Copper would be the hottest. Aluminum would be the second hottest, and water would be the third hottest. Okay, so how do we know that? And the answer is do experiments to find that out, okay? And there's a key uh, concept here that we're going to get to in just a second, but let's just remind ourselves what happens to the distribution of particles. Well, the particles heat up and they push their average temperature up higher. It just turns out that water does it much less than the others, right? So we might end up over here with the copper, we might end up, over here with the aluminum, and we might end up over here with the water, right? So how much they get pushed higher and higher and higher depends on their physical characteristics. Water is special in that it has very strong attractions between the molecules inside it. Well, you might say, but a metal does too. That's true. But the way that metals are made, essentially like positive atoms or positive ions embedded in a sea of negative charge, actually allows them to heat up very quickly for a minimal amount of heat input, right? The bonds, I guess, snugging them together when it comes to heat aren't quite as strong as they are with water. So let's look at the actual numbers involved here. So I'm going to just introduce a little nice formula here. So your temperature change is going to be based on a few things. So we'll call it delta T, right, because it's a change in temperature. And basically what that's going to be is C m over Q. Okay, did I do that right? Let me just double check. Sorry, let me just fix what I just said there. Formula that helps us work with this is Q equals MC delta T. I think I had these kind of upside down. Okay, so what do these values mean? Well, Q is the symbol for heat energy. So in this case, Q is going to be that 1 kilojoule we put in. M is the mass of the substance that we're putting heat into. Okay. T is how much the temperature changes, and that's what we're interested in, right? So this is temperature change. Remember, it's change of temperature. It's not telling you the final temperature, it's just telling you how much it changed, right? If we put heat in, temperature increases. If we take heat out, temperature decreases. Simple. By the way, again, heat always flows from hot to cold. If we just leave an object sitting that's very hot, after some time it will be cooler, and the surroundings will be warmer as the heat flows into them. And C is the specific heat capacity. So I'm going to give you a little challenge here. What units do you think Q is going to be measured in? Q, heat energy, measured in what? What's energy always measured in? It's okay to tell me. Yeah, joules. Okay? So the answer should be in joules. Mass. What is mass measured in? C, I'm not really sure what it's measured in. And what do you think delta T is measured in? Well, since it's a delta, it could be measured in either Kelvin or Celsius because they mean the same thing, right? So we could just say, we could say Kelvin or we could say degrees C. It's sort of irrelevant. Let's go just for fun here. Let's just do it Kelvin. Let's do it in terms of Kelvin. Okay. So my question is, what units must C then be measured in? I'll pause while you figure that out. Okay. So if you look, your answer needs to be in terms of joules, right? One of the input values is kilograms. So do you see kilograms over here? No. So part of the unit has to get rid of kilograms, right? So to get rid of kilograms, we might go per kilogram, right? That would cancel kilograms off. The other one is Kelvin. You don't see Kelvin over there, so you're going to get rid of them. And I don't see joules anywhere over here, so it must be joules. Well, actually, if we write it like this, it's joules per kilogram per degree Kelvin. Does that make sense? This is how many joules it takes to heat 1 kilogram of substance up 1 degree Kelvin. Does that make sense to you? How many joules to heat 1 kilogram of substance up 1 K? So, in the case of copper, from experiment, it turns out that copper takes 390 joules for every kilogram for every Kelvin. Aluminum takes a little more, 910 joules kilogram Kelvin. And water has a mind-blowing 4180 joules per kilogram per Kelvin. Okay? And we'll talk about water again next class and how something like the calorie would fit in there. But there's a specific heat. So now if we go over here and we look at our little formula, we should be able to figure out what we need to do to figure out our final values, right? So Q equals MC delta T. I feel like we're running out of time here. Remember that delta T is equal to the final temperature minus the initial temperature, right? So let's just rearrange this formula to help us solve. Right, so we could say then that TF minus TI equals Q over MC. And then that would just rearrange to be the final temperature equals whatever our value here is plus whatever our initial temperature was. Okay. So let's try it for the aluminum block. So Q, oh, sorry. I guess I can start putting numbers in. We said that we were going to put 1,000 joules in, right? So 1,000 joules goes in. The mass we said was 0.1 kg. Okay, and I think we said we were doing the aluminum one, right? Okay. So sorry, 0.1 kilograms, and aluminum is 910 units is joules per kilogram Kelvin. And again, remember, we're dealing in Celsius here, so Kelvin or Celsius is gonna be interchangeable in this concept. In a delta, it's interchangeable. So can we get a value for this? What do we get? It's basically like 10,000 divided by almost 1,000. So what should we get? Plus 20 degrees Celsius. It should be 31 degrees. Okay, 31 degrees Celsius. All right, you guys for homework can try the other two and see what you get. Okay?